At the heart of nearly every galaxy, a monster lies in wait. We call them supermassive black holes, and their existence is one of modern astronomy's greatest triumphs. Yet for every answer they provide, they unleash a dozen deeper, more profound mysteries. Today, we are going to explore 30 of the most compelling and unresolved puzzles surrounding these cosmic giants. By the end, you will have a front-row seat to the very edges of human knowledge, where physics itself breaks down. We will confront how something so immense could form almost instantly after the Big Bang, and what truly happens to matter that crosses the point of no return. What cosmic secret about our universe do you find most unsettling? Our first mystery strikes at the very beginning of everything. How do you build a cosmic giant almost from the moment the universe is born? The standard story for black hole formation is elegant and simple. A massive star, many times heavier than our Sun, lives a short, violent life before its core collapses in a supernova explosion. What remains is a stellar mass black hole, perhaps 10 or 20 times the mass of the Sun. From there, it must eat voraciously and merge with others to grow. But there is a problem, a cosmic stopwatch ticking against this idea. Astronomers have found the brilliant beacons of quasars, powered by supermassive black holes, shining from when the universe was less than 1 billion years old. For a stellar mass seed to grow to billions of solar masses in that blink of cosmic time, it would have to eat at an impossibly frantic, unsustainable rate, violating the very laws we think govern their growth. So how did they get so big, so fast, too compelling, yet utterly different? Theories compete to explain these impossible infants. The first is the stellar remnant path, a story of relentless consumption and merger. Imagine the first generation of stars, monsters made of pure hydrogen and helium. They could have been hundreds of times the mass of our Sun, burning fiercely and dying young. Their collapse could have created black hole seeds larger than the usual kind, maybe a few hundred solar masses. These heavier seeds would have a head start, but even they must feast almost constantly to reach supermassive status in time. The second theory is more dramatic, a shortcut written into the fabric of the early cosmos. This is the direct collapse model. Picture a primordial cloud of gas, vast and pristine, cooling and collapsing under its own weight. But in this unique environment, without the heavy elements that help clouds fragment into stars, it does not break apart. It collapses as one single monstrous entity. There is no star, no supernova, just a direct catastrophic fall into a black hole seed that could be 10,000. Even 100,000 times the mass of our Sun from its very first breath. This is a true cosmic titan born in a single event, a ready-made giant that needs far less time to grow into the quasars we observe. Both ideas have their own profound implications. The stellar remnant path suggests a universe where the first black holes were built slowly, brick by brick, through violent mergers and insatiable hunger. The direct collapse model implies that the seeds of today's galactic monsters were themselves colossal from day one, a product of the universe's unique initial conditions. Observations are closing in, searching for the faint signatures of these first seeds, but the question remains wide open. Did our galaxy's heart begin as the corpse of a single, unimaginably large star, or was it born from the direct, silent collapse of a primordial cloud? The answer rewrites the first chapter of cosmic history. This symbiotic relationship leads us directly to our second profound mystery, which came first, the galaxy or the giant at its center. It is the ultimate cosmic chicken or egg problem. Astronomers have discovered a startling and precise correlation. The mass of a galaxy's central bulge, that dense swarm of older stars at its heart, is almost perfectly proportional to the mass of its supermassive black hole. A larger bulge always hosts a heavier black hole. This is not a coincidence. It is a fundamental clue written into the structure of the universe, suggesting these two entities did not evolve independently. They grew up together, their fates inextricably linked across billions of years, but the question of causality remains maddeningly unclear. Did the galaxy form first, its vast reservoir of gas and stars eventually funneling material inward to feed and grow the central black hole? Or did a primordial black hole seed form early on, acting as a gravitational anchor whose powerful influence dictated how the galaxy assembled itself around it? The evidence points to a dynamic, two-way street. When a supermassive black hole is actively feeding, it becomes an active galactic nucleus, unleashing torrents of energy and powerful jets of material. This violent feedback can heat surrounding gas, preventing it from cooling and collapsing to form new stars. In this way, the black hole acts as a cosmic regulator, putting a brake on the galaxy's growth. It can even blow huge bubbles of gas out of the galaxy entirely, starving it of future star-forming fuel. So the black hole is not just a passive occupant. It is an active architect shaping the very galaxy that hosts it. This creates a delicate balance, a feedback loop of creation and destruction. The galaxy feeds the black hole, and the black hole, in turn, controls how many stars the galaxy can make. They are locked in a gravitational dance, partners in a cosmic story of growth. Yet we still do not know who took the first step. Did the dance begin with the galaxy's first stars, or with the silent gravity well waiting at the center? This cosmic partnership between galaxy and black hole is built upon a foundation of unimaginable density. But what lies at the very end of that gravitational plunge? This brings us to our third and perhaps most profound mystery, the true nature of the singularity. According to Albert Einstein's theory of general relativity, the ultimate fate of all matter falling into a black hole is not just to be crushed, but to be erased in the most fundamental way. The equations tell us that every single atom, every particle of light, all of it is funneled into a single point at the very center. This point is the singularity. It is a place of zero volume, yet it contains all the mass of the black hole. The result is infinite density. Our mathematics and our physics simply stop working there. The concepts of space and time, as we understand them, cease to have any meaning. It is a one-word answer to what is at the center, a breakdown. This is not just a mathematical curiosity. It represents the single greatest conflict in all of modern physics. On one hand, we have general relativity, which masterfully describes the force of gravity and the warping of space-time on the largest scales. It predicts this inevitable, infinitely dense point. On the other hand, we have quantum mechanics, the wildly successful rules that govern the behavior of the very small, of atoms and particles. Quantum mechanics abhors the idea of infinity. It insists that there is a fundamental limit to how small things can be, a basic graininess to reality itself. At the singularity, these two pillars of physics meet and utterly fail to agree. Gravity says everything collapses to a point. Quantum mechanics says that is impossible. So which one is wrong? The answer is likely that both are incomplete. To truly understand the heart of a black hole, we need a new theory that successfully marries the world of the very large with the world of the very small. We need a theory of quantum gravity. This is the holy grail of theoretical physics, and black hole singularities are its ultimate testing ground. Without it, the center of a black hole remains a blank spot on our map of reality, labeled "Here be dragons." But physicists have ideas. Some theories, like loop quantum gravity, suggest that the crushing gravity is met by a powerful repulsive force arising from quantum effects. Instead of a sharp, infinite point, the heart of a black hole could be a fuzzy, bubbling region of spacetime, often called quantum foam. It might be a bridge to another part of the universe or an entirely new state of matter. The singularity, in this view, is not an end, but a transformation into something our current language cannot describe. We are left staring into the abyss, knowing our tools are insufficient, yet compelled to ask, If infinity is not the answer, what unimaginable truth lies in that darkness? The terrifying finality of the singularity is not the only way black holes threaten our understanding of reality. There is another, more subtle way they erase things, leading to our fourth great mystery, the information paradox. This puzzle begins not with crushing gravity, but with a slow, cold whisper from the void itself. In the 1970s, Stephen Hawking made a startling theoretical discovery. Empty space, according to quantum theory, is not truly empty. It is a seething, bubbling sea of virtual particles, constantly popping into and out of existence in particle-antiparticle pairs. Normally, these pairs annihilate each other almost instantly, but Hawking realized something profound could happen at the very edge of a black hole, right at the event horizon. If one of these virtual particles falls across the horizon, its partner is left stranded outside. Unable to annihilate, the stranded particle becomes real. To an outside observer, it appears as a tiny bit of radiation slowly leaking from the black hole. This is Hawking radiation. Over unimaginable eons, this slow leak causes the black hole to lose mass, to shrink, and eventually to completely evaporate. It is a beautiful, unifying idea linking quantum mechanics, thermodynamics, and gravity, but it creates a catastrophic problem. The radiation Hawking described is purely thermal. It is random noise, like the static from a hot stove. It carries no specific information about what fell into the black hole. Whether you threw in a library of books, a star, or a collection of old tires, the Hawking radiation coming out would look exactly the same. And when the black hole finally vanishes, all that unique information about what made it seems to be erased from the universe forever. This is the paradox. Quantum mechanics has a sacred, unbreakable rule. Information is never destroyed. You can burn a book, but in principle, if you could collect every single ash particle and trace every photon of light and heat from the fire, you could theoretically reconstruct the book. The information is scrambled, but it persists. Hawking radiation appeared to violate this fundamental law. It suggested black holes were the universe's ultimate shredders, not just crushing objects, but deleting the very data of their existence. For decades, this paradox divided physicists. Hawking himself famously bet that information was lost, while others, like Leonard Susskind, insisted it must be preserved. The conflict cut to the core of whether our universe is ultimately predictable and orderly, or if black holes punch permanent holes in its logical fabric. Proposed solutions are as mind-bending as the paradox itself. One leading idea is the holographic principle. It suggests that all the information about everything that falls into a black hole is not lost inside, but is instead perfectly encoded on the two-dimensional surface of its event horizon, like a cosmic hologram. The three-dimensional interior we imagine is just a projection of that data. When the black hole evaporates, that information is slowly and chaotically released in the Hawking radiation, scrambled beyond easy recognition but not destroyed. Another, more violent solution is the firewall hypothesis. It argues that to preserve information, the event horizon cannot be the smooth, uneventful gateway general relativity describes. Instead, it must be a searing wall of high-energy particles, a literal firewall that instantly incinerates anything crossing it. This solves the information problem by saying the information never actually enters the black hole, it gets smeared onto the horizon. But it creates a new crisis by violating Einstein's principle that free-falling observers should notice nothing special as they cross the horizon. We are left with a stark choice, each option dismantling a pillar of our physics. Either information is truly lost, breaking quantum mechanics, or the gentle horizon of relativity is an illusion replaced by a destructive blaze. The information paradox is not just about data, it is about whether the universe keeps a permanent record of all that happens, and what terrifying price we must pay to ensure that it does. The paradox of lost information forces us to look more closely at the boundary where this drama unfolds. The event horizon is not a physical wall you could touch, but a mathematical point of no return. It is the invisible spherical shell surrounding a black hole where the escape velocity equals the speed of light. Cross this line, and not even light has the energy to climb back out. But this simple definition masks a zone of profound and bizarre physics. For a distant observer watching an object fall toward a black hole, a strange illusion takes hold due to extreme gravitational time dilation. As the object approaches the event horizon, its clock appears to tick slower and slower relative to the universe outside. Its light becomes redder and dimmer, stretched to longer, lower energy wavelengths in an effect called infinite redshift. To the outside viewer, the object seems to slow down, fading to a faint red ghost that never quite reaches the horizon. It appears to smear itself across the surface of the black hole for all eternity. Yet for the astronaut making the fall, their own experience is entirely different. They feel nothing special as they cross the horizon, at least according to classical physics. They would pass this mathematical boundary in a finite amount of time on their watch, pulled inexorably toward the crushing destiny at the center. This stark difference between perspectives, between what is seen and what is experienced, is a direct consequence of spacetime being warped beyond all familiar limits. It creates a haunting question: which perspective is real? Is the astronaut truly frozen at the horizon from the universe's point of view, or is our distant observation just a cosmic trick of the light? This leads to another deep mystery about the horizon itself, known as the no-hair theorem. This idea suggests that black holes are remarkably simple objects. No matter how complex the star, gas cloud, or spaceship that falls in, the resulting black hole can be completely described by just three properties: its mass, its electric charge, and its spin. All other details, the chemical composition, the shape, the pattern of matter, are lost forever. The black hole has no hair, a metaphor meaning it has no distinguishing features. It is the ultimate cosmic eraser, shaving away all complexity. But does it really? Many physicists now suspect quantum mechanics paints a far more detailed picture. Just outside the event horizon, extreme gravity interacts with quantum fields, potentially creating a turbulent quantum atmosphere. This thin, energetic layer might not be smooth at all. It could be a buzzing hive of activity where information about what fell in is temporarily stored or encoded, like a scrambled hologram. Future telescopes, looking for subtle flickers or signatures in the light from matter just before it vanishes, might one day detect this structure. The event horizon, then, may not be the blank, featureless membrane we once thought. It could be the most complex surface in the universe, a shimmering veil where the fate of information is decided, holding secrets we are only beginning to imagine. That slow leak of Hawking radiation is a cosmic whisper, but some black holes produce the loudest screams in the universe. This brings us to the mystery of quasar engines. Quasars are the most persistently luminous objects we have ever seen, outshining entire galaxies from the edge of cosmic time. Their brilliance is not the glow of stars, but the furious death cry of matter as it is devoured. The engine for this unbelievable power is the supermassive black hole's accretion disk. Imagine a vast, flat whirlpool of superheated gas and dust spiraling inward at nearly the speed of light. Friction within this maelstrom heats the material to millions of degrees, causing it to blaze with light across the spectrum before it finally vanishes over the event horizon. This process of converting matter to energy is staggeringly efficient. While a nuclear fusion reactor in a star converts less than 1% of mass into energy, the extreme physics around a black hole can achieve efficiencies of up to 40%. Matter is not just burned here, it is transformed with ruthless proficiency. But the true signature of a quasar and its deepest puzzle is not just the glowing disk. It is the pair of relativistic jets that often erupt from its poles, shooting out for thousands of light years at nearly light speed. These are not diffuse sprays of light, but incredibly narrow, focused beams of particles and radiation like cosmic laser pointers. How does a black hole, an object defined by its ability to trap everything, including light, produce these powerful, focused outflows? The answer appears to be a partnership between two immense forces, the black hole's spin and magnetic fields born in the churning accretion disk. As the disk rotates, it drags magnetic field lines with it, twisting them into a powerful, coiled structure. The black hole's own spin, if it is rotating rapidly, can further wind these fields into a tight knot of energy. Think of it like a dynamo, where the motion of charged plasma in the disk and the spin of the black hole itself generate a colossal electromagnetic engine. This system can tap the rotational energy of the black hole, a process theorized by physicist Roger Penrose, and funnel it along the polar axes. The magnetic fields act as a rigid funnel, collimating the superheated plasma into those astonishingly straight jets. They are cosmic particle accelerators on a scale we could never hope to build. Yet this magnificent violence raises a profound question. Why is our own supermassive black hole, Sagittarius, a star, so quiet? It has all the necessary parts: a black hole, some infalling gas, and presumably a magnetic field. Yet it is a faint ember compared to the infernos of quasars. The difference seems to be one of diet and stability. To become a quasar, a black hole needs a steady, massive influx of fuel, like a continuous river of gas from a galactic collision or a disrupted star. Our galactic center is in a relatively peaceful neighborhood with only occasional small snacks falling in. Furthermore, the stability of the magnetic funnel may be key. If the accretion is messy and chaotic, the magnetic fields may tangle and snap, preventing the formation of those stable, focused jets. A quasar, then, is a black hole in a state of perfect, violent storm, where the inflow of matter is precisely tuned to power a universe-shaking beacon. The mystery lies in the exact recipe for this storm. What precise combination of spin, magnetic field geometry, and fuel supply flips the switch from a silent giant to the brightest object in the cosmos? Understanding that threshold is not just about distant quasars, it is about predicting when our own galactic heart might one day unpredictably roar back to life. Those relativistic jets are more than just brilliant beacons, they are the universe's ultimate particle accelerators. This leads us to the mystery of the most powerful bullets in the cosmos, the source of ultra-high-energy cosmic rays. Cosmic rays are not rays of light, but a constant rain of atomic nuclei, mostly protons, striking our atmosphere from deep space. Most have relatively modest energies, but a tiny fraction are in a class of their own. These ultra-high-energy cosmic rays carry as much kinetic energy as a professionally thrown baseball, but compressed into a single subatomic particle. We are talking about energies millions of times greater than what our most powerful particle colliders, like the Large Hadron Collider, can produce. For over a century, their origin has been one of astrophysics' greatest puzzles. Where in the universe can nature whip a single proton up to such an insane speed? The prime suspects are the very jets erupting from supermassive black holes in active galaxies. The physics is staggering. Within those magnetically focused beams, particles can surf on colossal shock waves, getting a kick of energy each time they cross the shock front. Trapped by the intense magnetic fields, they bounce back and forth across the jet, gaining a little more speed with each pass, like a ball bouncing between two converging walls. Over time, this process, called Fermi acceleration, can propel a particle to velocities within a hair's breadth of the speed of light, endowing it with that almost inconceivable energy. But confirming this suspicion is maddeningly difficult. Unlike light, which travels in straight lines, cosmic rays are electrically charged. As they streak across the universe, they are deflected and scrambled by the weak but pervasive magnetic fields that thread the space between galaxies. By the time one finally strikes Earth's atmosphere, creating a cascade of secondary particles we can detect, it is impossible to simply look back along its path to see where it came from. The particle's origin is a scrambled message. To solve this, scientists must become cosmic detectives, looking for statistical clues. Massive observatories like the Pierre Auger Array in Argentina cover hundreds of square miles with detectors, waiting to catch the rare air showers from these ultra-high-energy events. Instead of tracing single particles, they look for patterns. When they map the arrival directions of many of these events, they find a faint but tantalizing correlation. The rays do not point back to random spots in the sky. They show a slight statistical excess pointing toward the locations of nearby active galaxies with powerful jets. It is not a smoking gun, but it is a compelling fingerprint at the scene of the crime. The mystery endures because the deflection is so great that even a ray coming from a relatively nearby active galaxy might arrive from a completely different part of the sky. We are left piecing together a puzzle where the pieces have been deliberately scattered. Unlocking this secret means understanding not just the engines that fire these particles, but the invisible magnetic maze of the cosmos they must travel through. Each ultra-high-energy cosmic ray that strikes our atmosphere is a messenger from one of the most violent places in existence, but its letter home has been torn to pieces by the wind. The universe's most powerful particle accelerators operate with a terrifying precision, but the galaxies that host them are not always so perfectly ordered. We find our next mystery in a place where the cosmic anchor seems to have slipped. At the heart of the giant elliptical galaxy Messier 87, the one famous for the first ever image of a black hole's shadow, lies a subtle but profound anomaly. The supermassive black hole, a beast with the mass of 6.5 billion suns, is not sitting at the precise gravitational center of its galaxy. It is offset, displaced by a tiny but measurable distance. This is the strange case of the off-center black hole, and it challenges a fundamental assumption that these giants are always perfectly seated at the dynamical heart of their galactic homes. How can something so unimaginably heavy not be at the center? The gravitational pull of a supermassive black hole is the defining force in a galaxy's core. Everything should orbit around it like planets around a sun. Finding one that is not perfectly centered is like finding that the sun in our solar system is drifting slightly to one side. It suggests a recent, violent disturbance, a cosmic event powerful enough to shove even a 6 billion solar mass object. Astronomers have two leading theories for what could cause such a shift, and both involve incredible violence. The first possibility is a dance with an invisible partner. The offset could be the sign that the black hole we see is not alone. It might be part of a binary system, locked in a slow, gravitational waltz with another supermassive black hole. As they orbit each other, the visible black hole would appear to wobble around the system's true center of mass, creating the observed offset. This scenario is a predicted outcome of galactic mergers. When two galaxies collide, their central black holes eventually sink to the new common center, but this process can take billions of years. During that time, they would orbit each other as a binary, potentially for eons before finally merging in a universe-shaking burst of gravitational waves. The slight offset in Messier 87 could be a snapshot of this epic, slow-motion dance. The second theory points to an even more recent cataclysm. Perhaps the black hole was given a literal kick. If two black holes of unequal mass finally did merge, the laws of physics dictate that the resulting single black hole can receive a powerful recoil. This happens because gravitational waves are not emitted perfectly symmetrically during the merger's final moments. The new, combined black hole can be shot out like a rocket, propelled at speeds of thousands of kilometers per second. In most cases, it would eventually fall back to the center. But if the kick was just right, it could be left oscillating around the core, a bell that was struck and is still ringing. The offset we see could be the black hole at the farthest point of its swing, slowly drifting back toward true center over millions of years. This mystery is more than a celestial curiosity. It forces us to question how galaxies settle after the most violent events in the universe. An off-center black hole means the very fabric of the galactic core is still adjusting, its stars moving under the influence of a gravity well that is not where it should be. It is a signpost of a recent trauma, a clue that the majestic, smooth ellipse of Messier 87 is the aftermath of a storm we are only now learning to read. If such a colossal object can be moved, what other secrets about galactic formation are written in these subtle gravitational tremors? The slight wobble of a giant hints at a history of collisions, but those mergers depend on a crucial missing link in the cosmic family tree. We have mapped the ends of the black hole spectrum with confidence. On one side, stellar mass black holes, the remnants of dead stars, ranging from a few to maybe 100 times the mass of our Sun. On the other, the supermassive behemoths, millions to billions of solar masses reigning at galactic centers. But what lies in the vast gulf between? This is the mystery of the missing intermediate mass black holes. They should exist according to our theories of how cosmic structures grow. They are the crucial stepping stones, the potential seeds that could have grown into the supermassive giants we see today. Yet finding them has proven to be one of astronomy's most stubborn challenges. Think of it like trying to understand the life cycle of elephants by only ever observing mice and fully grown adults, with no evidence of calves, juveniles, or adolescents. The intermediate mass range from about 100 to 100,000 solar masses represents that entire missing adolescence for black holes. Their absence creates a glaring hole in our story of cosmic evolution. How did the first small seeds balloon into the monsters we see in the early universe without leaving behind a population of middleweight black holes? There are two compelling places to hunt for these elusive objects, each with its own set of clues and complications. The first is within the ancient, dense star clusters known as globular clusters. These are spherical swarms of hundreds of thousands of stars, all bound together by gravity and orbiting our galaxy like ancient satellites. Their dense cores are perfect laboratories for stellar collisions and mergers. The idea is that over billions of years, stellar mass black holes could sink to the cluster's center, pair up, merge, and gradually build up mass through a slow chain of collisions. This process could, in theory, forge a black hole of a few thousand solar masses. Astronomers look for the telltale signs, the gravitational sway such an object would have on nearby stars, causing them to orbit at surprisingly high speeds in the cluster's heart. A few globular clusters like Omega Centauri and G1 have shown exactly this kind of frenzied stellar motion, hinting at a dark, massive heart. But the evidence is indirect, a shadow inferred from the dance of stars, not a direct observation of the dancer itself. The second promising hunting ground is in small, faint dwarf galaxies. These are the building blocks of larger galaxies like our own, and if every large galaxy has a supermassive black hole, perhaps their smaller ancestors host the intermediate mass precursors. Here, the search looks for the faint, scaled-down version of a quasar engine, a trickle of accretion producing a subtle X-ray glow or a tiny flare of radio emission. Objects like ESO 243-49, a dwarf galaxy with an X-ray source too bright and compact to be anything but a black hole, are prime candidates. Another is the famous HLX-1, an ultra-luminous X-ray source far from the center of its host galaxy, whose brightness suggests a black hole of at least 10,000 solar masses. Yet confirmation remains maddeningly difficult. The main problem is their quiet nature. An intermediate mass black hole in a globular cluster or a dwarf galaxy often has very little gas to eat. Without a steady diet, it does not produce the brilliant, unmistakable beacon of an accretion disk. It sits in the dark, its presence only betrayed by the subtle gravitational tugs on the stars around it. Distinguishing that tug from the collective pull of many neutron stars or a dense knot of stellar remnants is a monumental statistical challenge. Furthermore, if they do form through mergers in dense clusters, the very process that creates them can also eject them. When two black holes merge, the gravitational wave recoil can kick the new, heavier black hole right out of the cluster and into the emptiness of intergalactic space, leaving no one home to find. So the missing middleweights might be missing because they are hiding in plain sight, too dim to see clearly, or because they have been thrown from the very places we expect to find them. Their discovery would be a monumental piece of the puzzle, the long-sought link proving that supermassive black holes can grow from the bottom up. Until we hold that evidence, a fundamental chapter in the story of how monsters are made remains frustratingly blank. Even a monster can hold a secret rhythm. Beyond its mass and charge, a supermassive black hole possesses a hidden dynamic property, its spin. This is not a simple rotation like a planet, but a fundamental warping of reality itself. The mathematics describe a spinning black hole as a Kerr black hole, and its behavior is profoundly strange. The immense gravity of a rotating mass does not just pull on objects. It literally drags the fabric of space-time around with it, like a spoon twisting in a vat of thick honey. This effect is called frame dragging. Near the event horizon, space itself is forced to move in the direction of the spin. An object falling in would be caught in this cosmic whirlpool, compelled to orbit in the same direction whether it wanted to or not. There is a region outside the event horizon called the ergosphere, where this dragging is so powerful that nothing can remain stationary. Everything, even light, is swept along in the relentless current of twisted spacetime. This spin is not just a curiosity, it is a fossil record written in gravity, holding clues to the black hole's entire life story. The central mystery is determining just how fast these giants are spinning, and what that speed reveals about how they grew to such immense sizes. Did our galactic monster build itself through a steady, orderly diet, or through a series of violent, chaotic collisions? The spin holds the answer. Think of a figure skater pulling in their arms to spin faster. A similar principle applies to black holes. If a supermassive black hole grows mainly by steadily pulling in gas from a smooth, orbiting accretion disk, the incoming material adds angular momentum, spinning the black hole up. Over time, with a consistent flow from one direction, it can reach breakneck speeds, approaching the maximum rate allowed by physics. In this scenario, a fast-spinning black hole tells a story of a long, stable, and gluttonous feast. But there is another, more violent path. Galaxies and their central black holes often grow by merging. When two black holes spiral together and finally collide, their individual spins and the orbital motion of their dance combine in a complex gravitational calculation. The result is often a spin that is slower, even dramatically slowed down. If the incoming black holes come from random angles, their spins can cancel each other out. A slow-spinning supermassive black hole, then, might be the product of a chaotic, messy upbringing, built through a series of colossal crashes that left it with little overall rotation. So, by measuring the spin, we can read the biography of the beast. Was it a refined diner or a voracious brawler? The challenge is taking that measurement from millions of light years away. Astronomers have developed clever techniques to probe this hidden property. One key method involves studying the very edge of the abyss, the innermost stable circular orbit. This is the closest point to the black hole where material can still orbit before plunging irrevocably inward. The location of this orbit is controlled by the black hole's spin. For a non-spinning black hole, it is relatively far out, but for a rapidly spinning black hole where space-time is dragged fiercely inward, that final stable orbit can be pulled much closer to the event horizon. Matter can orbit faster and hotter before it falls. By carefully analyzing the X-ray light from the superheated inner edge of an accretion disk, scientists can infer how close that searing gas gets to the center. The spectrum of light holds a fingerprint of the extreme gravity and velocities involved, allowing them to estimate the spin. Observations so far reveal a fascinating spread. Some supermassive black holes, like the one in the galaxy MCG 6-30-15, appear to be spinning at nearly the maximum possible rate, suggesting a long history of steady, ordered accretion. Others show more moderate spins, hinting at a more turbulent past. Each measurement is a chapter decoded, a clue to the epic and violent history of galaxy building. The silent spin of a black hole, a twist in the void, is therefore a narrative of cosmic violence or cosmic order, waiting to be read in the faint, high-energy glow of its final meal. A quiet giant sits at the heart of our own cosmic home. Sagittarius, a star, the supermassive black hole anchoring the Milky Way, possesses the mass of 4 million suns. It is surrounded by swirling clouds of gas and even stars on plunging orbits that come perilously close. Yet it emits only a faint, flickering whisper of light, a mere ember compared to the roaring furnaces of quasars. This is the strange silence of dormant giants, and it presents a paradox. With so much potential fuel nearby, why is our galactic monster not feasting? What flips the switch between a slumbering behemoth and a universe-shining quasar? The answer lies not in the black hole itself, but in the chaotic physics of its dinner plate. For matter to blaze with the brilliance of a quasar, it must form a smooth, dense, and fast-flowing accretion disk. This requires gas to lose its orbital energy, allowing it to spiral inward in a coherent, organized fashion. Around Sagittarius, a star, and many other quiet black holes, the gas seems to be stuck in a state of unproductive chaos. One leading theory to explain this quiet is called an advection-dominated accretion flow. Imagine trying to start a campfire with a handful of dry, scattered wood chips tossed into the air. They are too spread out to burn together effectively. In this model, the gas near the black hole is extremely hot and tenuous. The particles are so far apart that when they do collide, they cannot radiate away their heat efficiently. Instead of glowing brightly, the frictional energy gets trapped within the gas and is simply carried or advected across the event horizon with it. The black hole swallows the heat along with the matter, resulting in a dim, inefficient meal rather than a brilliant blaze. It is a cosmic case of energy disappearing into the void before it can ever shine. But there is another, more active form of suppression. Magnetic fields, those invisible lines of force, may be acting as a cosmic gatekeeper. Gas falling toward the black hole is ionized, meaning it is electrically charged. Intense, tangled magnetic fields in the galactic center can exert pressure on this charged gas, propping it up and preventing it from collapsing into a neat, radiating disk. The gas might be stuck in a turbulent, magnetized cloud, held at bay just outside the point of no return. Occasional clumps might break through, causing the small flares we observe, but a sustained, bright feast is magnetically forbidden. This leads to a profound realization about the life cycle of galactic nuclei. A supermassive black hole is not simply on or off. It exists on a spectrum of activity dictated by the mode of its accretion. The violent quasar state requires a massive, sudden, and organized influx of fuel, perhaps from a galactic collision that funnels entire rivers of cold, dense gas directly into the core. The quiet state is the default, a stable condition where the fuel supply is trickling, hot, and disorganized. Our Milky Way is in a peaceful, mature phase of its life. The great galactic storms that could trigger a quasar epoch are mostly in its past. Sagittarius, a star, dozes, its immense power latent, waiting for the next cosmic delivery of cold, dense fuel to awaken its terrifying potential. This silence, then, is not an absence of power, but a sign of a galaxy living in a calm and stable era. The mystery we must now confront is what happens when that calm is shattered. That silence is a mercy, for what awaits any matter that does cross the boundary is a fate we cannot truly comprehend. The journey of a single atom falling past the event horizon is a descent into the greatest unknown in physics. We can trace its path only so far with our equations before they scream in protest and break. So where does it all go? The traditional answer, the one provided by Einstein's general relativity, is stark and terrifying. Once past the horizon, every possible path through space-time points inward toward the center. There is no stopping, no turning back. The atom is caught in an inevitable rush, accelerating as space itself flows toward the ultimate destination, the singularity. In this view, the journey ends in a cosmic trash compactor of infinite density. The atom and all the information it carries is utterly crushed out of existence, its structure erased at that point of zero volume. It becomes part of the black hole's mass, adding to its gravitational pull, but its unique identity is lost forever. This is the classical fate, annihilation at the heart of darkness. But many physicists believe this cannot be the full story. The conflict with quantum mechanics forces us to consider far more exotic possibilities. One of the most tantalizing is that the black hole is not an end, but a bridge. The equations for a rotating black hole, a Kerr black hole, mathematically permit a structure called an Einstein-Rosen bridge, more popularly known as a wormhole. In this speculative geometry, the singularity might not be a point, but a tunnel or a throat connecting our region of spacetime to another, potentially in a different universe entirely. The infalling matter would not be destroyed but transported. It is a breathtaking idea that every black hole could be a one-way passage to another cosmos, a creator of new realities. Yet this elegant solution comes with devastating caveats. Theoretical work suggests such a wormhole would be violently unstable. It would pinch shut faster than any particle could traverse it, collapsing the bridge before anything could cross. To hold it open would require a form of matter with negative energy density, something exotic and purely hypothetical. So while the mathematics allows for the possibility, the physics of our universe seems to forbid the journey. If not a bridge to elsewhere, perhaps the matter is transformed. This idea connects directly to the information paradox and Hawking radiation. In this quantum-influenced view, the event horizon is a seething layer of virtual particle creation. The energy to create the escaping Hawking radiation particle comes from the black hole's own mass. Therefore, the infalling matter, in a deeply indirect and scrambled way, could be seen as the raw material for that radiation. Its mass energy is converted over eons into the thermal glow that slowly evaporates the black hole. The atom is not preserved, but its fundamental energy is recycled back into the universe. In a sense, the black hole is a cosmic recycler, albeit one that utterly scrambles the blueprints. Its final sigh of Hawking radiation is the last faint echo of everything it ever consumed. The most radical theories go even further, suggesting the matter becomes part of the stage itself. In some approaches to quantum gravity, like loop quantum gravity, the singularity is replaced by a region of immense but finite density, a quantum bounds. Here, the crushing gravity triggers a repulsive quantum force. The infalling matter might not be destroyed but reborn. It could emerge in a new, expanding region of space-time, a baby universe budding off from our own. In this scenario, every black hole in our cosmos could be the Big Bang of another. The matter we see falling in provides the seed for an entirely new reality, with its own laws and dimensions forever separated from ours. Our universe, then, might itself be the interior of a black hole in a parent cosmos, a nesting doll of realities born from gravitational collapse. These are not just wild speculations, they are necessary explorations at the edge of knowledge. The fate of matter inside a black hole forces us to confront the very nature of reality. Is the universe a one-way street toward erasure, or a complex web of connections and transformations we are only beginning to map? The answer determines whether black holes are the ultimate endpoints of existence, or the most profound catalysts for creation in the multiverse. The silence of a dormant giant is not a permanent state, for the universe is a place of relentless collision and reunion. When two galaxies are drawn together by gravity, a slow-motion catastrophe unfolds over billions of years. Their stars, like swarms of fireflies, pass by each other mostly unharmed in the vast emptiness of space. But their central supermassive black holes are on an inevitable collision course. Dragged by friction with gas and stars, they sink toward the new common center of the merged galaxy, eventually forming a binary pair. This sets the stage for the most energetic event since the Big Bang, the merger of two supermassive black holes. As these cosmic monsters spiral inward, they churn the fabric of spacetime itself, sending out ripples known as gravitational waves. The final moments of this dance release more power than all the stars in the observable universe combined, concentrated into a fraction of a second of pure, vibrating gravity. Yet for all this theoretical fury, observing such an event directly remains one of astronomy's greatest challenges, wrapped in a stubborn puzzle called the final parsec problem. The issue is one of cosmic distance and diminishing returns. As the two black holes draw close, their gravitational influence clears out the stars and gas from their immediate vicinity. To spiral the final critical distance, they need to shed orbital energy, but with little left around them to provide friction, the binary can stall, with the black holes orbiting each other at a separation of about 1 parsec, a few light years, for a time longer than the current age of the universe. They become effectively stranded, a pair of titans locked in a perpetual, silent waltz, unable to take the final plunge. This theoretical gridlock contradicts what we believe must happen, for we see single supermassive black holes at the hearts of merged galaxies. Something must break the stalemate. The solution may lie in a third body, perhaps a third black hole from a previous merger, whose gravitational kick can disrupt the delicate balance and push the pair over the edge. Or it may require a fresh influx of gas late in the merger process, providing the necessary drag to tighten the final orbits. Solving the final parsec problem is essential to understanding how the most massive black holes in the universe ever came to be. While we have not yet heard the distinctive chirp of a single supermassive black hole merger, we are beginning to perceive their collective roar. Across the universe, countless such binaries are slowly inspiraling, each emitting a faint, steady hum of low-frequency gravitational waves. This creates a background sea of spacetime vibrations, a cosmic symphony of bass notes too deep for instruments like LIGO to hear. To detect this hum, astronomers have turned the galaxy itself into a telescope using pulsar timing arrays. These projects like NanoGrav monitor the clockwork flashes of millisecond pulsars, the universe's most precise natural metronomes. As gravitational waves wash through the galaxy, they minutely stretch and compress the space between us and these pulsars, causing their rhythmic pulses to arrive early or late in a predictable pattern. After decades of data collection, a signal has emerged from the noise, a low-frequency rumble consistent with the collective chorus of millions of supermassive black hole binaries. It is not the sound of one collision, but the statistical murmur of them all, the first direct evidence that these stalled binaries do, in fact, find a way to overcome the final parsec and continue their fatal dance. This background hum opens an entirely new sense with which to perceive the cosmos. It allows us to listen to the slow, grinding evolution of galaxies on the largest scales, to census the population of these hidden binaries, and to finally test the physics that drives them together. The mystery of the merger is no longer purely theoretical. It is a vibration we have begun to feel, a deep note in the soundtrack of the universe's violent gravitational heart. The gravitational waves from merging giants are a testament to the immense energy locked within a black hole's spin. But there is a place where that rotational power becomes tangible, a zone of pure, twisted force called the ergosphere. This is not the event horizon, but a larger, football-shaped region surrounding a spinning black hole, where the warping of space-time reaches its most bizarre extreme. According to Einstein's theory, a massive rotating object does not just sit in space. It drags the very fabric of space-time around with it. Near a rapidly spinning supermassive black hole, this frame dragging is so violent that space itself is forced to move at incredible speeds. Within the ergosphere, it is impossible to stand still. No object, not even a beam of light, can resist the current. Everything is compelled to move in the same direction as the black hole's rotation, caught in a cosmic whirlpool from which there is no stationary escape. It is a place where the concepts of here and there, of forward and backward, lose their familiar meaning, dictated entirely by the spin of the monster within. This strange property leads to one of the most ingenious ideas in theoretical physics, the Penrose process, a way to steal energy from a black hole itself. Conceived by physicist Roger Penrose in 1969, it is a thought experiment of cosmic larceny. Imagine a spacecraft, or more realistically, a single particle entering the ergosphere. Once inside, it splits into two pieces. One fragment is given a carefully calculated kick so that it falls across the event horizon, never to return. The other fragment, however, is propelled in the opposite direction, escaping the ergosphere entirely. Here is the miraculous result. The fragment that falls in is given a negative energy orbit relative to the distant universe. By dumping this negative energy into the black hole's mass energy actually decreases. The escaping fragment, meanwhile, carries away more kinetic energy than the original particle had when it entered. Energy has been extracted directly from the black hole's rotational momentum, slowing its spin ever so slightly. It is a perfect cosmic robbery, using the twisted physics of the ergosphere as the getaway vehicle. Could such a process explain the staggering power of real cosmic phenomena? While the Penrose process as described is too delicate and precise to account for the colossal jets from quasars, the fundamental principle extracting rotational energy via magnetic fields and plasma in the ergosphere is thought to be the engine behind those very jets. This is known as the Blandford-Zeenagic mechanism. Picture the magnetic field lines anchored in the black hole's accretion disk, twisted into a powerful coil by the frame dragging of the ergosphere. This creates a gigantic natural battery. Charged particles sliding along these lines can be flung outward at nearly light speed, tapping the black hole's spin to power jets that span galaxies. So in a very real sense, the most powerful engines in the universe are already running on stolen black hole energy, a scaled-up, magnetized version of the Penrose principle. This raises a tantalizing, far-future question. Could a civilization ever harness this power directly? The engineering challenges are, of course, beyond anything conceivable. It would require stabilizing an object inside the violent, chaotic ergosphere, precisely manipulating particles, and surviving radiation levels that vaporize matter. Yet as a theoretical possibility, it speaks to the raw power lying dormant in these spinning giants. A supermassive black hole's rotational energy represents a reservoir millions of times more efficient than nuclear fusion. For a civilization facing an existential energy crisis across cosmic timescales, a black hole would be the ultimate power plant, a gravitational dynamo that could fuel growth for eons. The ergosphere, then, is more than a curiosity of warped space. It is a frontier of extreme physics, a potential wellspring of cosmic power, and a permanent reminder that in the heart of darkness, even rotation can be a source of light. That potential for stolen energy hints at a universe crackling with unseen forces, and sometimes that energy announces itself in a sudden, brilliant scream. From the depths of space come the most transient and powerful radio signals we have ever detected, fast radio bursts. These are flashes of radio waves that last mere milliseconds, yet in that blink of an eye, they release more energy than our sun does in 80 years. They arrive from billions of light years away, and for over a decade, their origin has been one of astronomy's most captivating puzzles. While many sources have been proposed, from colliding neutron stars to evaporating black holes, one of the most intriguing possibilities ties them directly to the environments we have been exploring, the chaotic hearts of galaxies where supermassive black holes reign. The clues lie in a special subclass of these bursts, the repeaters. Unlike one-off events, these sources fire off multiple bursts over days, months, or years. Even more astonishing, some of these repeating bursts show a pattern. They cycle through periods of frantic activity followed by eerie silence, with the entire sequence repeating on a regular schedule, like a cosmic lighthouse with a broken, unpredictable lamp. This periodicity is a massive clue. It suggests the burst source is not a single cataclysmic explosion, but an object in a tight orbit around something else, its burst somehow triggered at the same orbital point again and again. This is where the supermassive black hole enters the story. Imagine a magnetar, a type of neutron star with a magnetic field 1,000 trillion times stronger than Earth. These are already cosmic powerhouses capable of immense outbursts. Now, place that magnetar in a close, whirling orbit around a supermassive black hole at the center of its galaxy. The environment becomes a pressure cooker of unimaginable forces. The black hole's immense tidal gravity could periodically stress the magnetar's crust, triggering starquakes that release pent-up magnetic energy in colossal radio bursts. Alternatively, as the magnetar plows through the diffuse gas and magnetic fields swirling around the black hole, it could create immense shock waves that accelerate particles, generating those brilliant millisecond flashes each time it passes through a particularly dense patch. The orbit itself provides the clockwork, explaining the periodic pattern of activity we observe. This hypothesis elegantly links two extremes, the stellar-scale fury of a magnetar with the galactic-scale gravity of a supermassive black hole. It provides a natural, repeating engine in the exact dense, violent environments where we expect such exotic pairings to exist. Yet for all its appeal, the mechanism remains deeply mysterious. We do not fully understand how a magnetar's magnetic energy converts into such a focused, spectacular radio burst, even in isolation. Adding the chaotic, extreme physics of a black hole's vicinity makes the puzzle infinitely more complex. The bursts could be caused by magnetic field lines snapping and reconnecting near the black hole, or by material from the magnetar itself being stripped away and violently accelerated. Each flash is a message from a place where physics is pushed to its breaking point, a place we cannot yet fully model. The search is on to find more of these periodic repeaters and to pinpoint their locations with exquisite precision. If they are consistently found right at the dynamical centers of their host galaxies, the evidence for the black hole connection would grow overwhelming. Each new detected burst is a piece of a code, a millisecond-long transmission from a magnetar screaming as it whips around a monster, telling us a story of gravity and magnetism written in radio waves. The furious energy of a magnetar's scream is a product of its immense magnetic field, a kind of cosmic hair that defines its identity. But what of the black hole it orbits? We are taught these giants are bald, defined by just 3 numbers. This is the no-hair theorem in its purest form: mass, spin, and theoretically electric charge. Yet this third property, electric charge, opens a door to a strange and largely invisible class of monsters, leading us to our 16th mystery. Can a supermassive black hole truly hold a significant electric charge? And if so, what would that even look like? The mathematics of Einstein's equations permit a solution for a charged, non-rotating black hole, known as a Reissner-Nordström black hole. Its structure is subtly but profoundly different from the familiar kind. Instead of a single event horizon, it possesses 2 concentric spherical boundaries. The outer horizon functions much like the one we know, a point of no return for infalling matter and light, but inside it lies a second, inner horizon. This inner boundary is a place of theoretical chaos, where the influence of the black hole's own charge becomes dominant. and the classical equations of general relativity are predicted to break down in what's called a Cauchy horizon instability. For an observer foolish enough to cross the outer horizon, the inner horizon might not be a wall, but a gateway to other regions of space-time, or a violent region of infinite blue shifted radiation. It is a mathematically fascinating but physically precarious object, so why do we never seem to find them? The universe appears to have a powerful preference for neutrality. Space is not a perfect vacuum. It is filled with a tenuous plasma of free electrons and ions. If a black hole somehow acquired a strong positive electric charge, it would immediately begin attracting negatively charged particles from this surrounding plasma. Like a cosmic magnet pulling in opposite charges, this influx would rapidly neutralize the black hole's charge. The process is thought to be incredibly efficient, draining away any significant net charge on timescales far shorter than the black hole's life. A charged black hole, in this view, is an unstable momentary state, a temporary imbalance quickly corrected by the cosmos itself. But could any process defy this neutralizing tendency? One speculative idea involves a black hole in an environment devoid of the usual neutralizing plasma. Perhaps in the early universe or in the void between galaxy clusters, a black hole could form with a primordial charge and maintain it if there is simply nothing around to cancel it out. More dynamically, consider a black hole feeding on a disk made of only one type of charged particle. While this seems fantastically unlikely for normal matter, some theories suggest exotic environments, like those around a magnetar or in the aftermath of certain particle physics events, could create such a biased diet. Even then, the charge would likely be fleeting. The observational signature of a charged black hole, however, would be unmistakable and dramatic. Its electric field would violently interact with any surrounding matter. Accretion would be chaotic, with positively charged gas being fiercely repelled if the black hole itself were positive, potentially creating lopsided, sizzling disks and unpredictable flares. Most tellingly, the intense electric field could become a particle accelerator of unimaginable scale, generating beams of ultra-high-energy charged particles and a unique spectrum of radiation that our telescopes could, in principle, identify. We have not seen such a clear signature yet, which reinforces the idea that nature abhors a charged black hole as much as it abhors a vacuum. The mystery of charge, therefore, is a question of cosmic cleanliness. It asks whether the universe's preference for neutrality is an absolute law, or if, in some forgotten corner or under some extreme condition, a black hole can wear a permanent electric crown. Finding one would not just add hair to the bald theorem, it would reveal a cosmos capable of sustaining imbalances we thought impossible, and open a window into the violent physics of those unstable inner horizons where time itself might fray. The universe may abhor a charged black hole, but it has no such qualms about absolute destruction. Occasionally, a star in the bustling core of a galaxy will stray from its safe orbit, wandering into the fatal grip of the central supermassive black hole. What follows is one of the most violent spectacles in the cosmos, a tidal disruption event. As the star approaches, the difference in gravitational pull between the side facing the black hole and the side facing away becomes overwhelming. This tidal force stretches the star horizontally while compressing it vertically, pulling it apart into a long, thin stream of gas in a process called spaghettification. The star is not swallowed whole, it is shredded. Roughly half of its remains are flung out into the darkness on hyperbolic orbits, while the other half forms a temporary, superheated accretion disk around the black hole, igniting a brilliant flare of radiation that can outshine its entire host galaxy for months. We have seen these cosmic fireworks, but each one poses new, intricate puzzles. The first mystery is one of temperament. Why do some tidal disruption events produce staggering, focused relativistic jets, while others simply glow as a brilliant, disorganized fireball? The difference seems to lie in the anatomy of the black hole and the geometry of the feast. If the black hole is already spinning rapidly and possesses a strong, ordered magnetic field, the incoming stellar debris can be channeled along its poles, powering those narrow, lightning-fast jets. If the black hole is slower or its magnetic environment is more chaotic, the gas simply forms a turbulent, glowing disk with no clear outlet, resulting in a bright but jet-less flare. The type of star matters too. A more massive, puffy star might provide too much fuel at once, choking the engine and preventing a clean jet, while a smaller, denser star could offer a more manageable stream. It is a cosmic recipe where the ingredients of spin, magnetism, and stellar composition combine to produce either a focused beam or a diffuse explosion. Another enigma is written in the light itself. Each flare has a unique light curve, a graph of its brightness over time, and a specific spectrum, the fingerprint of the chemical elements present. These details should, in theory, tell us everything about the star that was destroyed and the black hole that did the destroying, yet the observed patterns are wildly diverse. Some flares fade quickly, others linger. Some show strong hydrogen lines from a sun-like star. Others reveal the helium-rich core of a star that had already shed its outer layers. The exact shape of the light curve depends on a maddening number of factors: the star's initial trajectory, its internal structure, how quickly the debris circularizes into a disk, and even the viewing angle from Earth. It is as if we are trying to reconstruct the blueprint of a building by studying the pattern of its explosion from a single, distant vantage point. The final, crucial question is one of cosmic accounting. How much of the star is actually consumed by the black hole, adding to its mass, and how much is violently ejected back into the galaxy? Simulations suggest the process is incredibly messy and inefficient. While a significant fraction of the stellar gas eventually spirals in, a tremendous amount is flung away at high speed, carrying chemical elements forged in the star's heart back into the interstellar medium. This makes tidal disruption events more than just destructive. They are also agents of cosmic recycling, seeding future generations of stars and planets with heavier elements. Yet measuring this balance from our distant perch is extraordinarily difficult. We must infer the masses from the glow of the accretion disk and the faint echo of the ejected stream, a calculation filled with uncertainty. Each tidal disruption event is a fleeting, natural laboratory. For a few brief months, we get to watch the entire life cycle of an accretion disk, its formation, its peak brilliance, and its slow fade unfold in real time, a process that would take millions of years around a quasar. By studying these extreme, short-lived experiments, we can test our theories of how black holes feed, how jets are launched, and how gravity behaves at its most destructive. Every time a star is torn apart, it sends us a detailed report from the edge of the abyss, written in light and motion, waiting to be decoded. A shredded star's elements are scattered back into the void, but on a far grander stage, a single black hole can dictate the fate of an entire metropolis of galaxies. This brings us to the mystery of the cosmic thermostat, the role of supermassive black holes in galaxy cluster evolution. A galaxy cluster is not just a random scattering of galaxies. It is the universe's largest gravitationally bound structure, a city of thousands of galaxies swimming in a vast, thin sea of superheated gas known as the intracluster medium. This gas is unimaginably hot, reaching temperatures of tens of millions of degrees, and it glows faintly in X-rays. For decades, cosmologists faced a perplexing problem. Simple physics suggested this hot gas should be cooling down. As it radiated away its energy in X-rays, the dense gas at the cluster's heart should cool rapidly, flowing inward to fuel a frenzy of new star formation in the central galaxy. Observations, however, told a different story. The central galaxies in clusters are not the colossal star factories this cooling flow theory predicted. They are often quiet, aging giants full of old red stars. Something was preventing the gas from cooling, keeping the cluster's core on a steady, simmering boil. The prime suspect sits at the very center of that central galaxy, its supermassive black hole. The solution is a phenomenon we have seen before, but now operating on a truly gargantuan scale: active galactic nucleus feedback. Here, the black hole's jets are not mere beacons. They are the universe's most powerful heating systems. As the black hole feeds, it launches relativistic jets that plow into the surrounding intracluster medium. These jets do not simply pierce through, they inflate. They blow colossal, buoyant bubbles of radio-emitting plasma that can be hundreds of thousands of light years across, dwarfing the galaxy that hosts them. These are the cosmic equivalent of air bubbles rising in a pot of thick soup. As these vast radio bubbles slowly rise through the hot gas, they push it aside, creating ripples and shock waves that travel through the cluster. This turbulent motion transfers energy from the jets into the gas, reheating it and preventing it from cooling and collapsing. It is a breathtakingly elegant regulatory system. The black hole acts as a cosmic thermostat. When the central gas cools and begins to flow inward, it feeds the black hole. The black hole, in turn, becomes active, launching jets that heat the gas and shut off the fuel supply. The system then quiets down, allowing the gas to cool once more, and the cycle begins again. This feedback loop explains why clusters are not overrun with new stars. But the precise mechanics of this balance are a profound cosmological puzzle. The timing and energy must be exquisitely calibrated. Too little feedback, and the gas cools uncontrollably, creating a starburst of impossible scale. Too much feedback, and the gas is blown out of the cluster entirely, starving galaxies of the raw material for future generations of stars. Observations from telescopes like Chandra reveal the stunning complexity of this process. We see not just smooth bubbles, but intricate structures, ripples from ancient outbursts, cavities within cavities, and vast shock fronts racing through the gas. It suggests the black hole's activity is not a steady hum, but a series of powerful periodic eruptions, each one resetting the cooling clock for millions of years. The mystery lies in the trigger. What tells the black hole to switch on at just the right moment with just the right power? Is it a subtle change in the density of the cooling gas or the infall of a small galaxy? How does the energy from the narrow jets get so efficiently distributed throughout the enormous volume of the cluster core? This feedback is not a local event. It is the central black hole governing the climate of a cosmic continent, its outbursts writing the history of star formation for thousands of galaxies at once. Understanding this balance is key to understanding why the universe looks the way it does today, a place of ordered structures rather than a chaotic firestorm of cooling gas. If black holes are the universe's ultimate drains, then white holes are their impossible counterpart, cosmic fountains. They are a purely mathematical possibility arising from the same equations that predict black holes, but with time running in reverse. Where a black hole's event horizon is a one-way street inward, a white hole's horizon would be a one-way street outward. Nothing could ever enter a white hole from the outside. It could only spew out matter and energy that originated from within. It is the ultimate cosmic repulsion, a region of space-time that violently expels everything and cannot be entered. While no white hole has ever been observed, and many physicists doubt they could exist in our stable universe, their theoretical possibility opens a door to one of the most mind-bending ideas in all of cosmology. Could the interior of a black hole connect, via a tunnel through space-time, to a white hole in another location or even another universe entirely? This speculative bridge is known as an Einstein-Rosen bridge, or more popularly, a wormhole. In this interpretation, the terrifying singularity at the center of a black hole is replaced by a throat, a passageway. The black hole is the entrance, the white hole is the exit. Matter falling into the black hole in our universe would not be crushed into nothingness, but would emerge from the white hole somewhere else, perhaps in a distant region of our own cosmos or in a completely separate reality. This idea elegantly sidesteps the information paradox, as information would not be destroyed, merely relocated. It paints a picture of a cosmos stitched together by a web of these hidden tunnels, with black holes acting as portals. Yet this beautiful idea is plagued by profound instability. The mathematics suggest such a wormhole would collapse instantaneously, pinching shut faster than any particle or bit of information could possibly traverse it. To hold it open, to make it a traversable bridge, would require a form of matter with negative energy density, something exotic that pushes rather than pulls. While quantum theory allows for tiny amounts of negative energy in specific circumstances, the scale needed to stabilize a wormhole is far beyond anything we know. Furthermore, a white hole itself seems to violate the second law of thermodynamics, the principle that disorder always increases. A white hole, erupting with energy from seemingly nowhere, appears to be a source of order, a decrease in entropy. For it to exist, our understanding of cosmic evolution and causality would need a radical rewrite. So why does this mystery persist? Because it forces us to confront the deepest questions about time and the fate of information. If the universe truly forbids white holes and wormholes, it reinforces a strict, one-way arrow of time and the grim finality of the singularity. But if they are even remotely possible, it suggests a cosmos far more interconnected and creative than we ever imagined, where every ending might be a beginning somewhere else. The idea of a white hole as a cosmic fountain feels like pure speculation, but it forces us to ask what else might be hiding in the darkness. This leads to a mystery that touches the very foundation of the cosmos itself, the potential link between black holes and dark matter. For decades, we have known that most of the matter in the universe is invisible, a ghostly substance that does not emit, absorb, or reflect light. We call it dark matter, and we only know it is there because of its immense gravitational pull on galaxies and galaxy clusters. But what is it made of? The leading candidates have been exotic, undiscovered particles like WIMP, weakly interacting massive particles. Yet decades of searches have come up empty, leaving room for a radical, ancient alternative. Could dark matter be made of black holes, not the supermassive ones, but a vast population of smaller, primordial black holes, forged not from dying stars, but from the intense pressures of the Big Bang's first second? In the chaotic infancy of the cosmos, tiny, dense regions of space could have collapsed directly into black holes with a wide range of masses, from an asteroid's weight to thousands of suns. A cosmic sea of these ancient, invisible objects drifting between the stars could perfectly explain the gravitational grip of dark matter without needing a single new particle. This idea is compelling, but it comes with immense challenges. For these primordial black holes to account for all dark matter, there would need to be a staggering number of them. If they were too small, say the mass of an asteroid, they would have evaporated by now due to Hawking radiation. If they were too large, like stellar mass, their gravitational influence would have been noticed by now. They would disrupt star clusters, bend the light from distant stars in a specific way called microlensing, and leave other observable scars on the cosmos. So far, extensive searches for these microlensing events have ruled out primordial black holes as the sole explanation for dark matter across a wide range of masses. The window where they could still be a major component is narrowing to a very specific, elusive size, but the connection grows even deeper. If these primordial black holes did exist, they could solve another great mystery. They could have been the very seeds for the supermassive black holes we see in the early universe. A primordial black hole of a few thousand solar masses formed in the first instant would be a ready-made head start. It would sink to the center of a young galaxy and begin feasting, growing into a supermassive giant in far less time than if it had to start from a stellar corpse. In this scenario, dark matter does not just surround galaxies, it planted the monstrous hearts within them. There is another, more subtle interaction to consider. Even if dark matter is made of particles, its relationship with black holes is far from passive. Imagine the dense halo of dark matter that is believed to surround every galaxy, including our own. As individual dark matter particles orbit, some will inevitably pass too close to the central supermassive black hole and be captured. They would accumulate in a dense cloud around it, a dark matter spike. In some theories, when these particles collide, they could annihilate, producing a faint but steady stream of gamma rays that our telescopes might detect. Our own galactic center, with its quiet black hole, is a prime place to look for this eerie glow. Furthermore, this accumulated dark matter could provide a slow, steady fuel source for the black hole, influencing its growth over cosmic time in ways we have not yet accounted for. The mystery, then, is a two-way street. Are black holes themselves the hidden substance that shapes the cosmos, or are they merely the most powerful engines in a universe already dominated by an invisible, particle-based dark matter? The answer would rewrite our understanding of cosmic history from its very first moment. Each path leads to a profoundly different universe, one where the darkness is filled with ancient gravitational ghosts, or one where invisible particles whisper their secrets only in the violent neighborhood of a monster. The heart of a black hole is a place where time itself becomes a prisoner. The closer you get to that point of no return, the more profoundly time is stretched and warped by the monster's gravity. This is not a science fiction trope. It is a direct, bizarre consequence of Einstein's theory of general relativity, and it creates one of the most perplexing paradoxes in all of physics. Imagine two identical, perfectly synchronized clocks. One remains with a distant observer, safely watching from afar. The other is placed on a brave, or perhaps foolish, spacecraft that begins a slow, steady fall toward the supermassive black hole. As the falling clock approaches the event horizon, a strange thing happens to the light signals it sends back. From the distant observer's perspective, each tick of the falling clock takes longer and longer to arrive. The clock's hands appear to move in agonizing slow motion. The light from it reddens and dims, stretched by the immense gravity. As the clock gets infinitely close to the horizon, the time between its ticks, as seen from the outside, stretches toward infinity. To the distant watcher, the clock never quite reaches the event horizon. It fades to a faint, frozen ghost smeared across the surface of the black hole for all eternity. The falling object from this external viewpoint never truly crosses. Now, shift perspective to the astronaut carrying that clock inside the doomed spacecraft. Their experience is utterly different. For them, time passes at its normal, familiar rate. They feel no sudden jolt, no dramatic change as they cross the invisible boundary of the event horizon. On their watch, they pass that mathematical line in a finite amount of time, continuing their inevitable plunge toward the central singularity. Both perspectives are equally valid according to the laws of physics. This is the profound mystery of time dilation taken to its ultimate extreme. It forces us to ask a deeply philosophical question about reality itself. Which story is true? Does the astronaut truly cross the horizon and meet their fate, or are they forever suspended at the edge from the universe's point of view? The equations of general relativity provide a clear, if unsettling, answer. Both are true. There is no single universal now. What happens depends entirely on your frame of reference, your path through the warped geometry of space-time. For the universe at large, the infalling matter and light become a permanent part of the black hole's frozen surface, a fading fossil of its last moments. For the matter itself, the journey continues unabated. This leads to a staggering implication for the black hole's own evolution. From our external, distant perspective, does anything ever truly finish falling in? When we watch a black hole devour a gas cloud or a star, what we are really seeing over millions of years is the slow accumulation of those objects' last moments onto the apparent surface of the horizon. The black hole grows, its mass increases, but the process of ingestion from our point of view is an infinitely slow smear of time. This creates a bizarre picture of a black hole's history. Its exterior is layered like an onion with the infinitely time-dilated images of everything it has ever consumed, each forever trapped in the act of crossing. Yet, in the interior reality that we can never see, all that matter has long since reached the center. So, what is the true nature of the event horizon? Is it a genuine physical boundary where things happen, or is it a cosmic illusion, a trick of light and time played by gravity? This puzzle cuts to the core of what we mean by reality in a relativistic universe. If two equally valid observers can disagree so fundamentally on whether an event has occurred, we must accept that here and now are not absolute truths, but personal experiences shaped by gravity's relentless grip. Time itself may be a prisoner, but the space it flows through might be far stranger than we ever conceived. The singularity's infinite density is a mathematical warning sign, a place where our equations of gravity scream that they cannot handle the pressure. To find a way forward, we must shrink our perspective from the cosmic to the unimaginably small, to a scale where the very concepts of here and there dissolve into chaos. This is the domain of the Planck scale, a realm so tiny it defies everyday analogy. At distances of 10 to the negative 35 meters, a millionth of a billionth of a billionth of a billionth of a centimeter, the smooth, continuous spacetime described by Einstein's theory is predicted to break down. Quantum mechanics suggests that at this fundamental level, the vacuum of space is not empty and placid. Instead, it is a seething, turbulent ocean of potential. This is the theoretical concept of quantum foam. Imagine spacetime not as a still pond, but as a bubbling, boiling pot of water on the most furious setting. Tiny bubbles of pure geometry wormholes, tiny curled-up dimensions, and disconnected fragments of universe constantly pop into and out of existence. In this foam, the notions of a fixed location or a definite distance become meaningless. Space and time themselves become fuzzy and uncertain, governed by the same probabilistic rules that dictate the behavior of subatomic particles. This is the frontier where a theory of quantum gravity must take over from general relativity, and it offers a radical reimagining of the black hole's terrifying heart. Perhaps the singularity is not a sharp, infinite point at all. Instead, the crushing gravity of the collapsed star could be met by a powerful repulsive force arising from these quantum fluctuations. The collapse would not proceed to zero volume, but would halt at around the Planck scale, transforming the core into a permanent, churning knot of this quantum foam. In this view, the center of a black hole is not an end, but a transition into a new, fundamental state of matter and spacetime, a place where gravity and quantum mechanics are locked in a dynamic, frothy equilibrium. This idea could resolve the singularity problem elegantly. There is no infinite density because there is no true point. There is only this incredibly dense dynamic foam. The physics does not break down. It simply becomes a form we do not yet fully understand. Furthermore, this chaotic, interconnected foam could provide a potential escape route for information. In the bubbling geometry, tiny wormholes might fleetingly connect the interior to the exterior, or information could be encoded in the complex, shifting structure of the foam itself, eventually leaking out as the black hole evaporates via Hawking radiation. It is a compelling picture, one that replaces a dead end with a realm of vibrant, if incomprehensible, activity. Yet we must emphasize this remains deep in the realm of theoretical speculation. We lack a complete, tested theory of quantum gravity to confirm these stunning possibilities. The Planck scale is so inconceivably small that probing it directly is far beyond any conceivable experiment. We are inferring its properties from mathematics and the desperate need to solve the deep conflicts in our current physics. The quantum foam is a beautiful, hopeful idea, a vision that the heart of darkness is not an abyss of nothingness, but a cauldron of creation, where the fabric of reality is constantly being rewoven at its most fundamental level. It suggests that even in the ultimate collapse, the universe retains a spark of turbulent quantum vitality. The quantum foam churns at the heart of darkness, but to power a brilliant quasar, that chaos must be tamed and focused. That focus depends on an invisible force, a cosmic sculptor that guides the fury. The true power behind a black hole's most spectacular displays is not gravity alone, but magnetism. The immense magnetic fields threading an accretion disk are the secret conductors of the entire symphony. They perform two absolutely vital, yet seemingly contradictory tasks. First, they act as a cosmic brake, helping matter shed its orbital energy so it can spiral inward to feed the black hole. Second, they channel that liberated energy into the breathtakingly narrow, relativistic jets that scream from the poles. Without these magnetic fields, an accretion disk would be a sluggish, inefficient glow, and jets would never form. Yet for something so fundamental, we face a profound and basic mystery. Where do these immensely powerful magnetic fields even come from? The black hole's environment is not a perfect void. The interstellar medium, the thin gas between stars, is threaded with weak, primordial magnetic fields. These are faint relics, likely stretched and amplified over cosmic time from the early universe. One straightforward idea is that as vast clouds of this magnetized gas collapse to form an accretion disk, they simply drag these magnetic field lines inward with them. The field lines are frozen into the ionized gas, a principle known in plasma physics. As the cloud contracts and spins faster, the magnetic fields are compressed and wound up like twine wrapped around a spinning top, becoming stronger in the process. This could provide the initial seed field, a template of order drawn from the galactic chaos. But there is a major problem with this simple dragging model. The turbulence within an accretion disk is unimaginably violent. Superheated gas churns at near light speed, with immense shear forces as inner parts of the disk orbit far faster than outer parts. This environment is a perfect breeding ground for a magnetic dynamo. Think of it as a cosmic version of the dynamo that generates Earth's magnetic field in its molten iron core. In the disk, the turbulent motion of the conductive plasma can stretch, twist, and fold weak magnetic field lines. This complex motion can amplify a tiny seed field exponentially, building it into a dominant, organized force. The dynamo process is a bootstrap operation. Motion creates magnetic fields, and those magnetic fields, in turn, influence the motion, creating a self-sustaining loop of magnetic fury. This could mean the powerful fields we see are not imported, but are homegrown in the disk's own violent physics. The truth likely involves both processes in a delicate partnership. The weak interstellar field provides the initial seeds, the raw threads. Once those threads are caught in the accretion disk's furious whirlpool, the dynamo takes over, spinning them into a powerful, organized web. This magnetic web then solves the central problem of accretion, angular momentum. Matter in orbit wants to stay in orbit. It possesses spin energy that must be removed for it to fall inward. Magnetic fields provide the mechanism. They act like springs or levers connecting different parts of the disk. The faster spinning inner disk tries to drag the magnetic field lines, which are rooted in the slower outer disk. This creates a magnetic tension that acts as a brake on the inner material, slowing it and allowing it to fall inward, while simultaneously transferring that spin energy outward, pushing the outer parts of the disk to a wider orbit. It is an elegant transfer of momentum, mediated entirely by invisible lines of magnetic force. The ultimate proof of this magnetic architecture is the jet. The twisting, coiled magnetic fields near the black hole's poles become so intense that they act like the barrel of a railgun. Charged particles are accelerated along these rigid field lines, focused into beams of unbelievable power. The entire system, the feeding, the braking, the jet launching, is a single, interconnected magnetic machine. If we misunderstand the origin of the fields, we misunderstand the engine itself. This is why astronomers scrutinize the polarization of light from quasars and active galaxies. Polarization is the fingerprint of magnetic fields, telling us about their strength and geometry at the very brink of the event horizon. Each new observation is a clue to whether we are seeing the ghost of an ancient galactic field, or the signature of a self-made dynamo operating at the limits of physics. The power to outshine galaxies begins with a question we are still asking. Are these magnetic fields passengers, or are they the product of the storm? Deep within the flickering X-ray glow of a feeding black hole, a hidden rhythm sometimes emerges. It is a pulse, a rapid, almost musical oscillation in the brightness, repeating hundreds of times per second. Astronomers call these signals quasi-periodic oscillations, and they are among the most tantalizing clues we have to the violent physics occurring just outside the point of no return. This rhythmic flickering is not a steady metronome tick. It is quasi-periodic, meaning the signal drifts slightly in frequency and strength over time. It is the sound of a system under immense stress, a heartbeat that is irregular, frantic, and full of information. These QPOs are generated in the inner accretion disk, where gas, heated to millions of degrees, races at a significant fraction of light speed before its final plunge. In this region, the warping of spacetime by the black hole's immense gravity is so severe that the rules of orbital motion are rewritten. The mystery lies in decoding exactly what physical process is beating the drum. The leading theory connects these oscillations to fundamental orbital frequencies predicted by general relativity. In the flat space of our solar system, an object has one simple orbital period. But in the twisted spacetime near a black hole, an object can oscillate in three different ways simultaneously. It has an orbital frequency moving around the black hole. It can also oscillate radially, moving slightly inward and outward like a spring as it orbits, and it can oscillate vertically, bobbing above and below the plane of the disk. General relativity gives precise formulas for these three frequencies, and they all depend on the black hole's mass and, crucially, its spin. The idea is that some form of instability in the seething plasma, perhaps a clump of hotter gas or a standing wave in the inner disk, gets locked into one of these resonant frequencies. As it orbits, it shines brighter at a specific point in its path, creating the rhythmic flicker we detect. If we can match the observed QPO frequency to one of these predicted frequencies, we could, in principle, measure the properties of the black hole and the very shape of spacetime around it with extraordinary precision. This is the profound promise of QPOs, to use flickering light as a sonar to map the gravitational well right at the edge of the abyss. Yet the reality is far messier than the elegant theory. The central challenge is that we almost never see a single, clean frequency. We see multiple QPOs at once, a complex harmony of high and low notes that change with the black hole's feeding rate. One of the most puzzling patterns involves pairs of oscillations where the frequencies are in a simple ratio, like 3:2. This strongly suggests a resonance where one physical motion is driving or exciting another. Imagine pushing a child on a swing. If you push at just the right moment in the swing's natural rhythm, you create a powerful, resonant motion. Near a black hole, the radial and vertical oscillation frequencies can enter into such a resonance, potentially creating a stable, bright pattern that shines through the chaos. But which resonance and in which part of the disk? The answer depends on details we cannot see directly, like the exact density and magnetic field structure of the plasma. Different models place the origin of the oscillations at different radii, leading to different conclusions about the black hole's spin. It is as if we are listening to a complex piece of music played in a cavernous hall, trying to determine the exact size and shape of the room by the echoes, while the instruments themselves are changing tune. Despite the complexity, each new observation from telescopes like NASA mounted on the International Space Station brings us closer to a solution. By monitoring black hole binary systems in our galaxy as they go through outbursts, scientists can watch how QPO frequencies evolve in real time, correlating them with changes in brightness and spectral shape. This allows them to test models against a dynamic reality. The ultimate goal is to use these cosmic rhythms as a direct test of general relativity. Does the spacetime around a black hole truly obey Einstein's equations in this regime of extreme gravity, or do we see subtle deviations that hint at new physics? The quasi-periodic oscillation is a faint, rapid whisper from the last stable orbit, a coded message about gravity itself. Deciphering its full meaning would allow us to hear the true shape of the darkness. The rhythmic heartbeat of a black hole's inner disk is a testament to the three-dimensional stage upon which gravity performs. But what if that stage is far larger than it appears? Some of the most profound theories in physics suggest our universe is not limited to the three spatial dimensions we move through. This is the potential for extra dimensions, a mystery that could rewrite the rulebook for black holes entirely. In our everyday experience, we know up, down, left, right, and forward, backward. Time adds a fourth dimension, but it is one of duration, not space. Theories like string theory, however, propose a cosmos woven from tiny, vibrating strings. For the mathematics of this theory to work, these strings must vibrate in not just 3, but 10 or even 11 dimensions. The extra dimensions are not vast, empty spaces we could travel to. They are thought to be curled up or compactified on a scale a billion times smaller than an atom, hidden from our perception at every turn. Yet, if they exist, their influence might be magnified in places of extreme gravity, making supermassive black holes our most powerful potential telescopes into this hidden architecture of reality. One startling implication involves the end of a black hole's life. Hawking radiation, that slow quantum leak, arises from processes at the event horizon. In a universe with extra dimensions, gravity could seep into these hidden realms. This would effectively give the black hole more ways to evaporate, like a puddle drying out not just from the top, but from its sides into an unseen dimension. A black hole in such a cosmos could evaporate much faster than our standard three-dimensional physics predicts. An ancient, small primordial black hole from the Big Bang might have vanished already in a multidimensional universe, whereas it could still be lingering in a simpler one. The event horizon itself might look different. In 3 dimensions, the point of no return is a sphere. But if gravity propagates into extra dimensions, its grip could change shape at microscopic scales. The black hole's shadow, the dark silhouette we famously imaged, might carry a subtle fingerprint, an intricate pattern of light rings that betrays the existence of these curled-up dimensions. Perhaps the most provocative idea is that extra dimensions could lower the energy required to create a black hole. In our familiar three-dimensional world, compressing matter to form a black hole takes staggering, stellar-scale energies. But if gravity grows much stronger at extremely small distances by leaking into extra dimensions, then the energies achievable in a particle collider like the Large Hadron Collider could, in theory, be enough to create a microscopic black hole. It would evaporate instantly in a flash of Hawking radiation, a signature that would be the discovery of the millennium. While no such event has been observed, the search continues, a testament to how black holes serve as bridges between the cosmic and the quantum. The supermassive black holes at galactic centers are not just gravity wells, they are historical records. Their formation, their growth, and their very structure could encode secrets about the number and shape of dimensions that have existed since the dawn of time. By studying their properties with ever greater precision, their evaporation rates, the dynamics of matter just outside their horizons, the echoes of their mergers, we are indirectly testing the fundamental fabric of spacetime. They are natural particle colliders of unimaginable scale, performing experiments with gravity that we could never replicate. The mystery of extra dimensions asks us to envision a cosmos of breathtaking complexity, folded in upon itself, where the giants that rule the galaxies are also the most sensitive probes into the hidden folds of creation. The shadow we finally saw was not a hole but a profound silence. In April of 2019, a global collaboration of radio telescopes known as the Event Horizon Telescope unveiled an image that made history. It was the shadow of the supermassive black hole at the heart of galaxy Messier 87, a dark void encircled by a fiery, lopsided ring of light. This was not a photograph of the black hole itself, for that is impossible by definition. Instead, it was a picture of its absence, a silhouette carved from the very fabric of light and space. The dark central region is not the event horizon. It is something even more fascinating called the photon capture region. This is the zone where gravity becomes so overpowering that even light, traveling on the very edge of the event horizon, is forced into circular or plunging orbits. Any photon entering this zone is forever captured, creating a perfect darkness at the image's heart. The bright ring surrounding it is the tortured light from the superheated accretion disk. Some of that light escapes toward us, but a portion of it is bent by the black hole's gravity in a full loop, creating a luminous halo. The ring appears brighter on one side because the material in the disk is moving toward us at a significant fraction of light speed, its light boosted and brightened by a relativistic effect. The image was a triumph of human ingenuity, but for scientists, it was just the beginning of a deeper mystery. The precise size, shape, and asymmetry of that shadow and its ring are a cosmic diagnostic tool, a direct test of Einstein's general relativity in the most extreme environment imaginable. According to the theory, the shadow of a non-spinning black hole should be almost a perfect circle. The size of that circle depends directly on the black hole's mass. The data from Messier 87 matched the predictions with remarkable accuracy, confirming the mass estimates from other methods and providing a stunning validation of a century-old theory. But the real intrigue lies in the deviations from perfect symmetry. The slight flattening on one side, the exact thickness and brightness distribution of the ring, these subtle details are a coded message about the black hole's spin and the tilt of its accretion disk relative to our line of sight. A rapidly spinning black hole drags space-time so violently that it distorts the shadow, making it appear more oblong or D-shaped. By meticulously analyzing the ring's structure, astronomers can begin to map this spin, reading the biography of the monster from its silhouette. The ultimate mystery, however, is whether the shadow will ever show us something Einstein did not predict. As the Event Horizon Telescope sharpens its view and turns its gaze to other targets, like our own Sagittarius A star, it will look for any tiny anomaly in the shadow's shape. A shadow that is too small, too misshapen, or has an unexpected substructure could be the first hint of new physics. It might suggest that our understanding of gravity breaks down at the event horizon, or that exotic phenomena like a quantum froth or the influence of dark matter are leaving an imprint on the edge of darkness. That iconic image, then, is more than a portrait of a cosmic giant. It is a question written in light and shadow, asking whether the rules that govern our universe hold true at the very brink of the abyss. The shadow of a single giant is a profound silence, but the aftermath of a galactic collision can leave behind a pair of monsters locked in a gravitational waltz. This is the elusive hunt for binary supermassive black holes, two cosmic titans orbiting one another at the heart of a single merged galaxy. Theory tells us they should be everywhere. When two galaxies collide, their central black holes are destined to sink toward the new common center, drawn by friction with gas and stars. They should form a binary pair, circling each other for perhaps billions of years before their final cataclysmic merger. Yet finding these duos has proven to be one of observational astronomy's most stubborn challenges. How do you spot two invisible points separated by a distance smaller than a single pixel in our most powerful telescopes from millions of light years away? The search requires ingenious detective work, looking for subtle, indirect signatures in the light of their host galaxies. One of the most promising clues is a periodic flicker in the brilliance of a quasar. If two black holes are orbiting each other while actively feeding from a shared gas reservoir, their motion could modulate the accretion flow. Imagine two whirlpools spinning around each other in a bathtub, periodically stirring the water and changing the drain's efficiency. As the black holes move, their gravitational tug could rhythmically funnel more or less gas into their respective mouths, causing the quasar's overall brightness to rise and fall in a predictable, repeating pattern over months or years. Spotting such a clean, clockwork signal is the holy grail, but the reality is often messier, with competing signals from turbulent gas making the periodicity hard to confirm. Another telltale sign is a double nucleus. In some merged galaxies, high-resolution images reveal not one, but two distinct bright spots at the very center, separated by a few hundred light years. Each spot is a dense cluster of stars whipping around one of the black holes. This is a snapshot of the binary in its early stages, before the two giants have spiraled close enough to share a single, unified core. Yet even here, ambiguity remains. Are we seeing two black holes, or is one bright spot just a dense knot of stars without a dark heart? Confirmation often requires looking for the high-energy X-ray glow of hot gas being devoured by each candidate, a faint but distinct fingerprint of an active black hole. The deeper mystery lies in understanding the orbital dance itself. How do two objects, each with the mass of millions of suns, shed enough energy to spiral together? They clear out stars and gas from their immediate vicinity, and once that fuel for friction is gone, they can stall. This is the infamous final parsec problem. The binary may orbit for eons, separated by a distance that makes them virtually impossible to distinguish as two distinct objects. To overcome this stall, the galaxy itself must act as a mediator. A third, incoming black hole from another merger could give the pair a gravitational kick, pushing them closer. Or a fresh influx of cold gas late in the galaxy's life can provide the drag needed to tighten the final orbits. The fate of this dance is written in gravitational waves. As they spiral inward over millennia, the binary emits a steady, low-frequency hum of ripples in space-time. We have now begun to hear that collective hum from the universe, the background chorus from millions of such pairs. But the ultimate prize is to detect the distinct, rising chirp of a single binary in its final moments before merger. That signal would not just confirm their existence, it would open a new window into the most violent process in the cosmos, allowing us to witness the birth of a single, even more massive giant from the union of two. Until we isolate that singular chirp from the cosmic static, the binary supermassive black hole remains a ghost in the machine, a predicted consequence of galactic evolution that is still hiding in plain sight, its silent dance governing the fate of merged galaxies. The cosmic dawn was not a gentle sunrise, but a violent, transformative storm. For hundreds of millions of years after the Big Bang, the universe was a cold, dark fog of neutral hydrogen gas, an era aptly named the Cosmic Dark Ages. Then something happened. An immense flood of energetic ultraviolet light began to tear through that primordial fog, stripping electrons from the hydrogen atoms and reionizing the cosmos, rendering it transparent to light for the first time. This was the epoch of reionization, a pivotal chapter that shaped the entire future of cosmic structure. The mystery lies in identifying the primary architects of this great illumination. For decades, the first generation of massive stars was the leading suspect, their fierce ultraviolet radiation a natural tool for the job. But there is another, more potent candidate lurking in the early shadows, the the supermassive black holes blazing as quasars. Could these monsters, not stars, have been the primary floodlights of the young cosmos? The challenge is one of cosmic accounting on an unimaginable scale. To reionize the entire universe requires a staggering number of high-energy photons, and they must escape their sources to travel vast distances. Young, massive stars are prodigious producers of ultraviolet light, but they are often born within thick clouds of gas that can trap their own radiation. Their ionizing power might be brilliant, but it could also be localized, struggling to clear the universal fog. Quasars, however, are a different kind of beast. Powered by supermassive black holes gobbling matter at a ferocious rate, they are thousands of times brighter than an entire galaxy of stars. Their radiation is not just intense, it is focused into powerful beams and can punch through surrounding gas more effectively. A single, brilliant quasar could act as a cosmic lighthouse, its beam carving out vast, transparent bubbles in the neutral hydrogen for millions of light-years around it. To solve this mystery, astronomers must become cosmic census takers at the very edge of observable time. They search for the most distant quasars, those whose light has been traveling for over 13 billion years to reach us. Finding them is like looking for a single, specific lighthouse on a distant, fog-shrouded shore from the other side of an ocean. Each discovery is a monumental feat. These quasars appear not as majestic swirling galaxies, but as faint, red pinpricks of light, their signatures stretched and redshifted by the expanding universe. By studying their spectra, the detailed fingerprint of their light, scientists can measure how much of their energetic radiation is escaping, and crucially, they can see the shadows cast by the remaining patches of neutral hydrogen fog along the line of sight. It is a direct measurement of the quasar's environment and its ionizing power. The picture emerging is complex and humbling. The most distant quasars found so far do appear to be surrounded by large ionized bubbles, proving they were potent agents of change in their immediate neighborhoods. Yet the census also reveals a critical problem. There simply do not seem to be enough of them. In the first billion years of the universe, brilliant quasars appear to have been relatively rare. While each one was a powerhouse, their collective contribution to the global reionization effort may have been limited, like a few scattered spotlights trying to illuminate an entire continent. The bulk of the work likely fell to the countless dimmer but far more numerous first stars and small galaxies whose combined ultraviolet glow, though individually weaker, could have permeated the cosmos more uniformly. This leads to a deeper, more subtle question. Perhaps the role of supermassive black holes was not to provide the majority of the photons, but to act as catalysts and pioneers. Their intense beams could have carved out the first major clearings in the neutral fog, creating pathways for the light from early stars to travel farther. They might have jump-started the process in dense regions, their radiation triggering waves of star formation that then produced more ionizing light. The mystery of reionization is no longer a simple either-or question. It is about understanding a cosmic partnership between stellar furnaces and gravitational monsters, a collaborative effort to transform a dark, opaque universe into the transparent, star-filled expanse we see today. The search for ever more distant quasars continues, each one a probe into that ancient era, helping us weigh the contribution of the universe's most violent engines in its most important transition. The paradox of information screaming to be saved found its most elegant answer in a principle so strange it redefines reality itself. This is the holographic principle, and it begins with a simple, almost absurd question. How much information can you fit inside a room? Intuitively, you might think the answer depends on the room's volume. A bigger room can hold more books, more hard drives, more atoms. But in the 1970s, physicist Jacob Bekenstein made a startling discovery about black holes. He found that the maximum amount of information, or entropy, a black hole can contain is not proportional to its volume, but to the area of its event horizon. The surface area, not the vast interior, sets the ultimate data limit. It was as if a library's capacity was determined by the square footage of its walls, not the cubic space inside. This bizarre area law hinted at a deeper truth. Perhaps everything within a volume is not truly three-dimensional at its most fundamental level. Perhaps the interior is an illusion, a projection. Think of a common hologram like the shimmering image on a credit card. It appears to have depth and solidity, a full three-dimensional object, but all that information is actually encoded on a flat, two-dimensional plastic surface. Scatter the hologram into pieces, and each fragment contains a blurry version of the whole image, not a single part of it. The holographic principle applies this logic to the universe itself. It proposes that all the information about every particle, every force, every event happening within a region of space, like the entire interior of a black hole, is not stored within that volume. Instead, it is perfectly and completely encoded on the lower dimensional boundary of that region. For a black hole, that boundary is the event horizon. The three-dimensional drama of infalling stars, swirling gas, and the mysterious interior is just a holographic projection from the data painted on the two-dimensional surface of the horizon. Every atom that falls in leaves an imprint there, like a pixel being added to an immense cosmic screen. This solves the information paradox with breathtaking elegance. Information is never lost inside the black hole because it never actually enters in the traditional sense. It is transferred and stored on the horizon. When Hawking radiation slowly evaporates the black hole, that encoded information on the surface is gradually, chaotically released back into the universe, scrambled beyond easy recognition but never destroyed. The principle does more than rescue data. It suggests a radical rewrite of physics. It implies that our experience of a three-dimensional world with depth and solidity is a grand illusion. The true, fundamental description of reality might be written on a vast, distant two-dimensional surface at the edge of the cosmos. We and everything we see are like shadows on the wall of Plato's cave, complex projections from a simpler, flatter reality. The equations of quantum gravity and general relativity find a meeting point on this holographic screen, a place where the fabric of spacetime itself emerges from quantum bits of information. The event horizon is not a destroyer of information, but its most faithful archivist, holding the complete story of the black hole's contents in a form we are only beginning to learn how to read. The holographic principle paints a cosmos where information is eternal, but the universe itself may not be. Our final mystery stretches the imagination across timescales that dwarf the entire history of everything we know. We must look trillions upon trillions of years into the far future, to the ultimate fate of the supermassive black holes themselves. According to Stephen Hawking's great insight, no black hole is truly permanent. That faint, slow leak of Hawking radiation means every single one, even the mightiest galactic giant, is on a cosmic clock, evaporating particle by particle back into the void. For a supermassive black hole like the one at the heart of our galaxy, this clock ticks with almost incomprehensible slowness. The process will take not billions, but 10 to the power of 100 years, a 1 followed by 100 zeros. This number is so vast it has no name. It is longer than all the seconds that have passed since the Big Bang, longer than the future lifespan of every star that will ever shine. It is an epoch of pure, dark domination known as the black hole era. Imagine a universe that is profoundly old, cold, and empty. All stars have long since burned out. Galaxies have evaporated as their stars drift apart into the endless expansion. The only sources of light, of structure, of anything at all, are the fading embers of these ancient black holes, glowing with their faint Hawking radiation in an ocean of absolute darkness. Yet even these last bastions of order are slowly dissolving. The evaporation is not a steady process. As a black hole loses mass, it gets hotter and radiates faster. A supermassive black hole spends eons as a cold, nearly dormant object, but in its final moments the process accelerates violently. The last 1,000 years of its 10 to the 100-year lifespan would see a runaway explosion. What happens in those final seconds is one of the greatest unknowns in theoretical physics. Does the black hole simply wink out of existence, leaving nothing behind? Or does it end with a catastrophic burst of energy and particles, a final shout containing all the scrambled information of everything it ever consumed? Some models suggest the evaporation culminates in a brilliant flash of high-energy gamma rays, the last of the black hole's mass energy converting into radiation in an instant. Others, considering quantum gravity effects, propose something even stranger. As the black hole shrinks to near the Planck scale, the realm of quantum foam, it might not vanish but transform into a stable, microscopic remnant, a fossil of infinite density, a permanent knot in space-time that contains all the original information frozen for eternity. This endpoint is not just about black holes, it dictates the ultimate destiny of the cosmos itself. After the last black hole evaporates, the universe enters what cosmologists call the dark era or heat death. This is a state of maximum entropy where no energy gradients exist, no work can be done, and no complex structures can form. It is a thin, cold soup of elementary particles and photons stretched across an infinite, expanding void. Time itself may become meaningless as there are no events to mark its passage. In this bleak, far future vision, the supermassive black holes were the last great structures, the final chapters in the story of complexity. Their slow evaporation was the universe's last sigh, yet even here mysteries persist. Could quantum fluctuations in this near-empty void, over timescales beyond imagination, spontaneously give birth to a new cosmos? Does the information locked in those final black hole remnants somehow seed a new Big Bang? The ultimate fate of these giants forces us to confront the deepest questions of existence, from the permanence of information to the very arrow of time. In a future so distant it makes the age of the stars feel like the first spark of a match in an endless night. We have traced the life of a cosmic giant from its impossible birth to its final cold whisper. 30 profound mysteries, each a frontier where our knowledge meets the abyss. From the infant quasars shining impossibly early to the silent, off-center wobble of a displaced monster. From the singularities' infinite paradox to the holographic screen where information is eternally saved. We have seen how these entities are not just destructive ends, but creative forces sculpting galaxies, heating cluster gas, seeding the universe with elements, and perhaps even birthing new realities within their depths. They are the ultimate laboratories where the two great pillars of modern physics, general relativity and quantum mechanics, meet and shatter against one another. Every question answered peels back a layer to reveal a deeper, more fundamental puzzle. They are not merely cosmic vacuum cleaners. They are the universe's most precise instruments, probing the nature of time, the architecture of dimensions, and the very meaning of information and reality. Their story is in essence our story, a quest to understand where we came from, what binds the cosmos together, and what ultimate fate awaits all of creation. So we turn the question to you. After this journey to the edge of understanding, which mystery lingers in your mind? Is it the terrifying fate of matter past the event horizon, the cosmic hum of merging giants, or the holographic idea that our reality is a grand projection? Let us know in the comments below. Share your thoughts and your own theories. If you crave more deep dives into the universe's greatest enigmas, be sure to subscribe. Our exploration of space mysteries has only just